Today we will start a new part of design of reinforced concrete sections. We have section with double reinforcement. If you remember, if you go back a little bit, area steel for the main reinforcement. Main reinforcement. Area steel bar for compression reinforcement. And we have two depths right now. The first one, depth for the main reinforcement called D. We have another depth for compression reinforcement called D prime. When I need to add compression reinforcement, if your concrete cross section not enough, we have limited depth of concrete cross section, so we need to compensate this shortage of concrete by additional reinforcement on the compression side, in the compression side. So if the size of the beam is restricted, then compression steel may be required. Yeah, this information is important. If compression steel is used, additional tensile steel must be added. I'm not sure what you mean by this point. Can you watch this one? You add here 3 number 9 bar. Single reinforcement. We have only reinforcement on one side. What will happen if you keep your reinforcement at the bottom the same and you add additional reinforcement to number 9 at the top? Nothing will happen. No increase in the beam capacity. No enhancement in the design of this cross section. Why? Because your steel reinforcement without compression reinforcement is the same when you add compression reinforcement. If compression steel is used, additional reinforcement must be added to that tensile reinforcement. So to get increase in your capacity, if you add to number 9, your bottom reinforcement must be 5 number 9. So this cross section will improve capacity. This is a definition of this sentence. Beam with compressive steel are more ductile. Additional compression steel reduce long-term deflections. Anybody remember what is the meaning of long-term deflection? Do you remember something called creep? Creep, you have constant load, but your beam deformation increase with time. Your load is constant, but deflection increase by time. This is called long-term deflection due to the effect of phenomena called creep. Compression steel reinforcement can be used to support stirrups. We have stirrups, we will talk about stirrups after exam 1 for shear. To hang these stirrups, we need compression reinforcement. So to design or to get your design moment, which called MN, for compression, for concrete with double reinforced section, we can divide this cross section to two cross sections. The first one, without any reinforcement in compression, we have reinforcement in tension with area steel 1. This cross section looks like the normal cross section we learned before. The second part, we have remaining reinforcement, which called area steel 2, with area steel bar. Both of them will give you another capacity. If you add this part plus this part, you can get the total capacity of the original cross section. Let's watch this one. We have cross section, looks like this. We have bottom reinforcement. We have top reinforcement. Do you think where is the tension side and where is the compression side? We have steel reinforcement here, we have steel reinforcement here. Which side is in tension, which side is in compression? The more reinforcement, the tension side. So we have more reinforcement down, your tension is down, your compression is up. In between, we have something called neutral axis. Do you remember what is the depth of neutral axis? C. Just a little above your neutral axis, we have compression block in concrete, and the concentration of this block called capital C, and this value of stress 0.85 F prime C. Anybody remind me what is the value of capital C? Volume of this block. I forgot something. What is the depth? A. What is the width? B. What is the volume? 0.85 F prime C A B. That's right. We have tension, capital T, in your bottom reinforcement. Can anybody remind me what is the value of T? Yeah, area steel at bottom, time F yield. Actually, at the top, we have compression force or compressive force in concrete, and another compressive force in the steel reinforcement in compression. So we can call this one CC and this one CT or CS. C steel reinforcement, C concrete. What's the name here? CS and CC, yes. So CC will not change. It's a volume of this compressive block. What is the value of CS? Any force in your steel equal your steel area time F yield. We will assume yielding in steel in compression steel. If compression steel yields. So we have force in concrete, we have force in steel, tension force, we have another compression force in steel in compression. Do you agree? Remember, we have here steel reinforcement. So we have compression in steel. We have compression in concrete. We have tension in steel. Your cross section is in equilibrium. That means CC plus CS equal T. If you apply summation f of x equals C. So 0.85 F prime C AB plus area steel prime F yield equal area steel F yield. The only unknown in this equation, your depth A. And from A, I can figure out what is the value of C. As you know, A equal beta 1 C. Any question so far? I think the same steps, but I add a new compressive force CS on the steel reinforcement in compression and put it in your equilibrium equation. And I can get the depth A, which can let me know what is the depth C.
We have two arrows there, but are they at the same location away from the neutral axis? Because the way you drew it looks like it's a little bit above.
This one and this one?
Yeah.
This one, at distance from the top, equal D prime at the location of your steel reinforcement. At this location. So depth of CS at D prime. This one. And location for the second one, CC, at the center line of this block at depth A over 2. So this distance for CC at distance A divided 2. Okay? As you remember, I told you, your cross-section, original cross-section, we have area steel, we have A prime steel. This area steel, part of it with the concrete cross-section, this part called area steel 1. Then the remaining part of area steel, which called area steel 2, with area steel prime. So we have two parts. First part, area steel 1 with concrete. Second part, area steel 2 with area steel bar. First part, your nominal moment of resistance equal area steel 1 F yield times D minus A divided 2. You got A. What is the value of area steel 1? Area steel 1 is a part of area steel. Area steel 1 equal total area steel minus area steel bar. Because this one must equal this one. So I know area steel 2. Because it's equal area steel bar. So area steel 2 plus area steel 1 equal area steel. So if you subtract area steel minus area steel 2, which is equal area steel bar, you can get area steel 1. So area steel 1, I can get it. F yield, depth, A divided 2, I can figure out what is the value of A. So I can get the nominal moment of the first part. Second part. Your nominal moment from the second part equal your area steel in compression time F yield time D minus D prime. The final moment for the whole cross section with reinforcement in tension and compression equal first nominal moment from the first part plus nominal moment from the second part. Once you are done with the total Mn, your design moment equal Mn time phi, and phi equal 0.9. Let's do an example. But remember, I assumed your compression steel yields. This assumption, we need to check this assumption first. Do you know how can I check this assumption is correct or not correct? Okay. Let's go back to this diagram. Do you know what is the meaning of this diagram? Strain distribution. At the top, we have something called epsilon C ultimate for concrete according to ACI equal 0.003. At location of steel reinforcement in compression, we have epsilon called epsilon steel bright, strain in steel in compression. At the bottom, at location of your steel in tension, we have something called epsilon tension or epsilon steel, whatever. I would like to check this value of strain. So we have two triangles. First triangle, the biggest one. This is your distance C, not X. And the second triangle, this little one. Okay, remind me. This value divide from the first triangle. Divide this value from the second triangle. So 0.003 divide epsilon steel bright equal. This distance from the first triangle, which called C, divide this distance from the second triangle. Anybody can tell me what is this distance will be?
D minus D prime?
No, C minus D prime. This little distance called D prime.